Welcome to the quantum software session. And our first talk will be given by Yuwei from Rutgers University. And the talk will be exploring the regular structure of modern quantum architectures for compiling and optimizing programs with permutable operators. I think you can get started.
Okay. Hi, everyone. My name is Yuwei. I'm a PhD student from Rutgers University. Today, I'm going to share our work exploring the regular structure of modern quantum architectures for compiling and optimizing programs with permutable operators. Quantum chips such as Google Sigma and IBM HyperX exhibit regular patterns in qubit connection. Google Sigma is shaped like rotated 2D grid, and IBM HyperX consists of several dodecagons. So we leverage this regularity to streamline the compilation of QoA programs. QoA is a hybrid quantum classical parameterized algorithms that exploit the strengths of quantum computers to solve optimization problems, like MaxCut. The goal of compilation is to construct a circuit satisfying the physical connectivity constraint with less gate count, circuit depth, and high circuit fidelity. For the input problem graph, vertices are encoded as qubits, and edges are encoded as 2-qubit gates. 2-qubit gates commute with each other, so they can be scheduled in any order between 2 layers of single qubit gates. Here is another valid circuit corresponding to the same input. So we can move the gate G2 to the front, let it run in the layer 1, and the circuit still produce the same outcome. For the same input problem graph, different circuit has different compilation results. This is the example of compilation of QoA program in a linear nearest neighboring architecture. The blue edges are SOP gates, used to solve physical connectivity constraint. Less is better. Physical circuit 1 has 4 SOP gates and circuit depth is 7. Physical circuit 2 has 2 SOP gates and the circuit depth is 5. So obviously here, circuit 2 is better. Compiling QoA circuit is hard. It has exponential number of choices of circuit to compile. This adds another degree of freedom for compiling QoA programs. So our approach begins with compiling the input of a click graph within a regular architecture, achieving linear bounded circuit depths. Implication 1, if we can solve an n-click QoA circuit, we can solve any subcircuit of the n-click circuit. Clicks graph is a complete connected graph. Implication 2, a solution for a small-scale problem could be generalized to solve a large-scale problem. So we designed an optimal solver that can handle small cases in special scenario. Here is an example of such compilation in a linear architecture. Coincidentally, it has the same shape as Abraham-Weismann's permutation network. So we can see here, in cycle 1, 3 gates are compiled corresponding to 3 edges in the input click graph. And in cycle 2, 2 more gates are compiled. And gradually, all 2-qubit gates are compiled. We then extend this method to more complex yet regularly structured architectures by leveraging the divide-conquer scheme. We unitize the complex architecture and divide the compilation problem into 3 sub-problems: auto interaction within a unit, bipartite auto interaction between 2 adjacent units, and every 2 units adjacent to each other. First, we consider how to achieve auto interactions in a 2D grid architecture. We divide each row of qubits as a unit. The unit movement could be achieved through transversal swap gates and following the linear pattern to make each unit adjacent with each other. The auto interaction within a unit could still be achieved by following the linear pattern. For the bipartite auto interactions between 2 units, we could apply the linear pattern swap sequence on the top unit and the alternative swap sequence on the bottom unit. For the Google Sigma architecture, we still consider 1 row of qubits at the unit, and the unit movement is still the same as 2D grid. The interaction between two units and within a unit could be solved by the linear pattern again if we combine two units as one. So in this architecture, we have more optimizations. Please refer to our paper. And we use A-star optimal solver to find such linear pattern and bipartite outward interactions between two units. We explore the A-star search tree with priority queue. The search tree starts from the root node. It means all gates remain unexecuted. Each edge stands for the execution of one possible combination of gates, including swap gates or C-phase gates. And all gates run in parallel. The cost is one cycle. Including the root node, each state node in the tree represents the status of circuit, including the remaining gates and the current qubit mapping. If we find a node that all gates are executed, we terminate the search process. The search process is guided by a cost function, f of node v. It equals to the sum of C of v and H of v. C of v is the cost of reaching the current node v, and H of v is the estimated cost of the remaining circuit, considering the degree of nodes of uncompiled input graph and the minimum swap cost for each uncompiled gate. Next, let's talk about how do we adapt the outward pattern to practical problems. The first factor is how do we adapt the outward solution to practical architectures like IBM heavy hex. IBM heavy hex is sparse, so we could apply the linear pattern to the longest Hamiltonian path, shown in red here. This could achieve outward interactions in the red path. And we also perform some interactions between the path qubits and off-path qubits on the fly. For the interaction between off-path qubits, we could swap those off-path qubits with the nearby path qubit and do the linear pattern again. With two iterations of linear pattern, we could achieve outward interactions in IBM heavy hex architecture. The input problem graph could be sparse. If we stick to the outward pattern, it will introduce some redundant swap gates and make the circuit depths unnecessarily long. So except that, we also need to consider the qubit error variability. With the consideration of these two factors, we propose our compilation framework. Starting from the input problem graph and the architecture graph, it does the initial mapping and generate the candidate gate list from the input problem graph. Then it has two major components, the pattern component and the greedy component. In the pattern side, it generates the predefined pattern, checks the remaining uncompiled circuit, and record the circuit depth and the gate count. The greedy component will check if it is efficient to follow the pattern. If not, it will stop the current pattern and insert swap gates heuristically. Once the qubit mapping is modified by the greedy process, the pattern generator will generate the pattern with the new qubit mapping and check the depth and gate count again for the remaining circuits. So in the end, the selector will check each data point saved and output the circuit with the minimum circuit depth, gate count, or highest circuit fidelity. For the experiment, we mainly consider two architectures, Google Sycamore and IBM heavy hex. We compare our method with three baselines, polyhedral, QAIM, and Toucan. We evaluate the performance of four methods with three metrics, circuit depth, 2-qubit gate count, and total variant distance. For the benchmarks, we use Python library network X to generate a random graph and a regular graphs with different density. The number of vertices is from 64 to 256. For the comparison on the IBM heavy hex architecture, our method has better performance than two baselines, QIM and polyhedral, on gate count and circuit depth. In these two figures, the x-axis are benchmarks and the y-axis are depth and gate count. Especially when the size of the input problem graph is large, our advantage is more significant. since our method guarantees the linear upper bound of the circuit depth. On the Google Sigma architecture, our method still performs better than two baselines. In these two figures, the x-axis are still the benchmarks and the y-axis are depth and gate count. We also compare our method with the state-of-art toucan on heavy hex architecture and has better performance. Some entries from toucan here is missing due to the compilation overhead. We did experiment on the real machine, IBM Mumbai. In this figure, x-axis is the optimization iteration and y-axis is the expectation value. Lower is better. Our method can produce the circuit with less gate count and shorter depths. So in the real machine experiment, the result of circuit converge faster and has better expectation value. Our method has the linear compilation overhead with respect to the QoE graph size because the pattern is predefined and the tracking pattern takes constant time. For the conclusion, we proposed the QoE compilation framework with linear bounded circuit depths. We introduced all-to-all interaction pattern for 4 architectures, linear nearest neighboring architecture, 2D grid, IBM HFX, and Google Sigma architecture. Our compilation framework has the adaptation for practical factors, such as the sparse input graph. And thank you.
If you have any questions, you can come here. I can ask one question, like in the last slides you mentioned, there are some architectures you can directly spot. For example, if there are some failure qubits on their architecture. So I know like Google Sycamore architecture at the beginning, they have some dead qubits on their hot wall. And when the scale gets larger, I guess you may have more like failure qubits on your hot wall, which may break the architecture you have at the beginning. And can your methods be easily extended to handle that cases?
Yeah, for now, my method cannot adapt that situation because we consider the whole architecture and because our method depends on based on the auto interaction because we consider the input is the click graph. So it could be our further research project. And I think we could also like do the graph partition on the input problem graph first, and so we can map the different part of the graph to the different part of the architecture to avoid the failure qubit. Yeah, thank you.
Okay. Any other questions? I can ask another one.
Yeah.
So I think overall it's a very interesting topic because QAOA is one of the most promising applications on near-term like Nixon machines, and try to find some application-specific compilation strategy to boost the performance. I think it's a good, very nice direction. I'm just curious, like after you do like this kind of interesting work, how far do you see like we can push it further towards like practical, some kind of like more practical things for this kind of applications in the next era?
I think
it's a little bit hard problem.
Yeah. I think it depends on the hardware, the error rate of the qubits. If the error qubit of the qubits is low, then we could run the large problems on the machine. Like for the most experiment in our paper are done on the simulation because like for the input problem graph with 256 qubits, it's impossible to run such application in the current hardware. So I think how far we can go, it depends on how good the machine we can build. Thank you.
Thank you. So our next speaker.
Loading. Awesome.
Okay, great. Our second talk will be from like Dawei Ding from DAMO Academy. The talk will be on one gate scheme to rule them all, introducing a complex yet reduced instruction set for quantum computing.
Hi, everyone. I'm David, and this is joint work with my co-authors, Jianxin, Weiyuan, Cupjin, and Qi. And we were formerly from Alibaba Quantum Lab. So the crux of our paper is something what we call quantum CRISC. So CRISC is short for complex yet reduced instruction set computer. It is complex in the sense that it includes all possible 2-qubit instructions, modulo single-qubit instructions. And it's also reduced in the sense that you don't pay any additional hardware overhead for having such an expressive instruction set. And you might think this is very counterintuitive. How do we have both complex and reduced for an instruction set? This is because quantum computing is fundamentally different from classical computing the following way. So classical gates we know is implemented by fabricating these physical transistors on a chip. So if you want more gates, more expressive instruction set, you need to have more complicated hardware. But for quantum gates, we apply these signal pulses like microwave pulses or lasers to this physical device we call a qubit. So this means that you can just have more complicated programming for different gates, and you can have a more expressive instruction set without paying hardware cost. So that's why we can have both complex and reduced. And the main reason we can do this is something called we call the ASH-N gate scheme. So a gate scheme is a physical procedure to implement a unitary operation on a hardware device. So the ASH-N gate scheme is a unified gate scheme. There's one type of physical operation that can implement any possible 2-qubit gate up to single-qubit gates. And this is a game changer because we know that both in many applications, we only assume that you have an individual CNOT, like a CNOT 2-qubit gate, or maybe ISWAP. But now we can have all possible 2-qubit gates with no additional hardware overhead. And we will see that at first, this is the maximally possible diverse set of gates for 2-qubit operations. And is also, we'll see that it's extremely useful for circuit compilation and other applications. So first, I'll go through a quick preliminary. We're going to talk about the vowel chamber. So vowel chamber is coming to this concept of local equivalence classes of SU4. So we know that on hardware, single qubit gates can be implemented with very high fidelity. So we kind of think of them as free resources. So that's why we have this concept that these 2-qubit gates can be equivalent if you can transform them to each other using single qubit gates. So for example, C0 and CZ are locally equivalent. So we want to make that mathematically precise. So we have something called a KAK decomposition for SU4, which basically states that you have this 2-qubit gate, a 4x4 unitary matrix, and you can decompose it in the following way. On the left and right are these going to be single qubit matrices, single qubit gates. And in the middle is something we call a canonical 2-qubit gate, which is the matrix exponential of a linear combination of X tensor X, Y tensor Y, and Z tensor Z. So the nice thing about this decomposition is that you can prove that this eta is the coefficients of these linear combinations. It's a 3D real vector. This eta describes the local equivalence class of U. So all the same SU4 that are locally equivalent has the same eta. And this eta lives inside the space, which we call the vowel chamber, which looks like this. It looks like this 3D tetrahedron. You can see very familiar 2-qubit gates, such as identity or swap or CNOT. These are actually the local equivalence classes of these gates. So for example, C0 and CZ will map to the same point in the bottom right corner. Okay, so now I'm going to go into the ASH-N gate scheme itself. So the Hamiltonian, so we assume we have a specific hardware device. The device is what we assume is a 2-qubit resonant interaction with transverse coupling and external drive. So that's a mouthful. What that looks like in hardware, at least for superconducting qubits, is the following. You have these, looks like a regular circuit, but these are superconducting, and the X's are Josephson junctions, which are nonlinear inductors. So they're kind of like LC oscillators. So like the LC oscillator on the left, LC oscillator on the right, these are our 2 qubits. And then they have some capacitive coupling in the middle. And they each also have an external drive. So there's a drive 1 that's driving the first qubit, a drive 2 driving the second qubit. And these drives are just going to be sinusoidal. Like these are very easy to implement on hardware electronics. So A1 is going to be the amplitude of drive 1, and omega D is going to be the frequency of drive 1. We happen to find that these two drives having the same frequency is sufficient for this. And one last thing, you also need to tune the qubits to have the same frequency. That's what we call a resonant interaction. So the Hamiltonian that you get looks like this. It looks like a bunch of terms. The first term, x tensor x, y tensor y, is coming from that capacitive coupling. G is the strength of that coupling. So the x tensor I is the drive from the first one. It's causing this x rotation. And the coefficient is the amplitude. And then I tensor x is drive on the second qubit. And then for the z tensor I and I tensor z is actually coming from the tuning, or we call the frequency difference between the drive frequency and the qubit frequency. So these qubits have their own frequencies, just like LC oscillators that have frequencies. And delta is the difference of those frequencies. So just wanted to say that even though this is inspired by superconducting qubits, this works for any Hamiltonian that has the same structure. Any hardware device that has the same Hamiltonian. So the main result is, given this Hamiltonian, we can now tune these different parameters. Like you can tune the amplitude of your drive, you can change the frequency of your drive, you can also change the evolution time, how long you evolve your qubits for. And then thereby we can prove that you can directly implement any element of SU4 modulo SU2 tensor SU2. And just to remind you, that's that tetrahedron space right here. The different colors are actually corresponding to different regimes. So if you're very fast to see this, A1, A2, delta T, that's 4 parameters, but this valve chamber is a 3-dimensional space. So there's over-parameterization going on here. So this green, for example, corresponds to when delta equals to 0. And then this blue is when A1 equals to A2. You have to take away 1 degree of freedom. So what's the nice thing about this is for the green and blue regions, we can prove that you can actually get to those gates, 2-qubit gates, in optimal time. So there's a lower bound proof in 2001 saying that if you have a target 2-qubit gate and a given 2-qubit Hamiltonian, there's a lower bound on how long you have to evolve that 2-qubit Hamiltonian to get to that target gate. And we're able to hit that lower bound. And that's a very good thing because we want our gates to be fast. We don't want decoherence. So we want them to be as fast as possible. And we're able to achieve that. So the red part is something technical part of this work, is that saying that if you want to do everything in optimal time, minimal time, you have to have infinitely large amplitudes. That's not physical. We can't have infinitely large amplitudes in the lab. That's why we have to do this trick. So you can imagine the valve chamber is like exponential x tensor x. It's a periodic structure. So if you, for example, can you see my cursor? Yes, okay. So for example, if you evolve from identity to C naught, but if you keep evolving, it starts going backwards because of this periodicity condition. And you end up in this red region. And by doing that, you forsake optimal time, but you no longer have unbounded amplitudes. And we can make this red region very small in practice. And we show that for superconducting qubits, these amplitude parameters for making the red region small is very reasonable. So we want to use these SU4 gates now for circuit synthesis. This actually inspires new compilation problems. So for example, we know that there's a lot of work in synthesizing 3-qubit, 4-qubit, n-qubit unitary gates using C naught. And here, A is for analytic, so you can prove that 20 C naughts is enough to get an arbitrary 3-qubit gate. N is numerical, so you can show that 14 C naughts, you can do some numerical optimization over single qubit gates, and you can make the fidelity very low, like 10 to the minus 10 or 14. L is a lower bound. You can do some dimension counting and prove that for 3-qubit gates, you need at least 14 C naughts to compile. And similarly for 4-qubit gates and for n-qubit gates, we actually do this. There's already a known like recursive kind of construction where you express n-qubit gates in terms of n-1 qubit gates, n-1 in terms of n-2, and so on and so forth. And then you add up all the gates together, and that's how we get the analytic upper bound there. So we do the same thing, but for SU4. If you can do all possible 2-qubit gates, how many do you need to get a 3-qubit gate or 4-qubit gate? We see that around, we get like a 50% gate reduction, which is pretty good. We don't need as many C naughts or 2-qubit gates as we thought. And this all comes down to this new construction that our interns figured out, that you can have these 2-qubit gates that can compile an arbitrary 3-qubit gate. So this is actually a very fundamental question, like how many 2-qubit gates do you need to compile a 3-qubit gate? And no one has actually answered that question or even asked that question because they didn't realize that you can actually do all these 2-qubit gates in hardware natively. And now that we showed that, we can ask that question. So you can see here, the V's are arbitrary 2-qubit gates, and deltas are diagonal 2-qubit gates. And different V's and deltas are different. It's not like they're the same V appearing here. And in the middle is a CZ gate. So you can prove that this is actually enough to get an arbitrary 3-qubit gate, and that's 11 right there. And we use that for our results. So there's also some follow-up work that we did, and we can generalize this instead of that really complicated specific Hamiltonian that we considered there. You can now replace that with any 2-qubit Hamiltonian as long as it has some coupling terms like x tensor x or something. And you can also tune the single qubit terms. You can get the same conclusion. You can get all of the vowel chamber in minimal time. And that's pretty cool because you know that if you want to do 2-qubit gates, you have to have a coupling term in your Hamiltonian. And if you want to do single qubit gates, you need to have these tunable single qubit terms in your Hamiltonian. So this comes to this very surprising result that I can conclude with the sentence here is that any hardware device, as long as it can natively support all single qubit gates and a particular 2-qubit gate, which means you have tunable single qubit terms and a coupling term in your Hamiltonian, that is already good. You need that for universality. You need all single qubit gates and a fixed 2-qubit gate. If you have that, that's already enough to support all possible 2-qubit gates up to local equivalence in minimal time. And that is it. Thank you.
Any questions? Yes.
Thank you for the talk. I'm Aditya. I have a question regarding the architecture that you made.
Mhm.
Do you think it's possible to use a similar type of architecture to natively create 3-qubit gates?
Yeah, so we're also looking into that right now. You can like turn on these couplings between like 3 qubits at the same time and add drives and see what gates you can get. But I don't think you can get all possible 3-qubit gates because that's too many degrees of freedom.
So you think it will be reduced from SU8 to some lower group?
Excuse me?
You think it'll be reduced from SU8 to some lower group?
Yeah, it'll be a smaller group though.
Okay.
Yeah.
Thank you.
I have one question. So generally speaking, like in real life, we still need to do a lot of calibration for each of the gate we want to
Yes,
start.
exactly.
If you really have this kind of continuous gate sets, I feel like it's kind of a little bit empirical.
Yeah.
Okay. Yeah. So do you see there's a middle end, like have selecting a small number of gates from this set, but you still can get almost the same like good result?
Yeah. So the nice thing about our gate scheme is a unified gate scheme. It's always like turn on the coupling, tune the qubits to frequency, same frequency, and add drives. It's the same physical procedure. So you can kind of do like an interpolation. It's like if you have this gate here with these parameters and this gate here with these parameters, you can kind of interpolate. But we also give in our paper a nice calibration procedure, which is basically answering the question, how do you calibrate an arbitrary 2-qubit gate? We know how to calibrate like CZ or ISWAP, they're very simple. But if you want to arbitrate 2-qubit gate, it might be more complicated. And using this thing, I won't go into the details, but basically the takeaway is that you can do phase estimation, quantum phase estimation, to directly measure the vowel chamber coordinates. So as long as you want to, if your final goal is not to do CZ or C0, but any like 2-qubit gate with the same vowel chamber coordinates, you can just do benchmarking or characterization here to get the vowel chamber coordinates directly through measurement, instead of getting all 15 parameters through QPT or something.
To this end, I have another question, very interesting work again.
Mhm.
So like in your like final theoretical study, you mentioned like for different kind of, if we want to have arbitrary gates, and the benefit of your work is super clear. But I want to know for practical applications, especially those we are using there, they have limited types of gates we want to have there. For those kind of gates, what is your benefit? Maybe
Yeah.
like C0 is just their native gates, like in the program. Okay, so I want to like understand practically how much benefit are we having there? Do you have some idea?
Yes, we are working on that right now. It's going to be a follow-up paper. And in general, we see a lot of gate reduction for like Hamiltonian simulation or VQE, where you have these really weird 2-qubit gates, which you need usually like 3 C0s to compile, but you can do directly using the ASH-N gate scheme.
Thank you for the talk. You mentioned that having access to arbitrary 2-qubit gates is sufficient to achieve these gate reductions for 3-qubit and 4-qubit gates. But I'm wondering, like, is there a smaller set of 2-qubit gates that is necessary to achieve this benefit?
Oh, that's a good question. I have not thought about that, but I will think about that.
Okay, thank you.
Next talk, like our next speaker is Yuwei. 10.
I'm sorry. Okay. Thanks for the introduction. I'm Siwei Tan, a PhD student from Zhejiang University. My advisors are Jianxin, Professor Jianxin, and Professor Li Qianglu. And today I'm going to present our work to achieve high confidence in quantum assertion validation. Quantum program verification is a fundamental method to ensure that the quantum program has correct behaviors. In the runtime verification, the expected functionality of the program is described as an assertion. An assertion consists of one or multiple predicates to check the runtime state and the relation between states. The assertion is true when no bugs are identified. To make it more clear, we present an example of the assertion in classical program. For the function that calculates the square root, we assert its input should be equal or greater than 0. The quantum assertion is similar to the classical assertion. It also validates the states of the qubits during the program, where the qubits usually stay in the superposition state. Besides, when making the decisions in the verification, confidence is very important. Confidence refers to the probability that the correctness of the program holds for all possible inputs. Exhaustive testing the assertion on every possible input is inefficient, especially for quantum computing. To ensure high confidence without low overhead, the ability to generate the validation result of the test inputs to the whole input space is necessary. Here we use a quantum example to motivate this ability. Given a quantum program, we test 99 inputs and find no bug. We stored the testing and think that the program is correct. Without the generalization ability, we can't use this 99 inputs to verify that the 100 input is wrong or not. So all of our effort is waste if the program is wrong. Overall, a good assertion method should have several properties. First, it should allow specifying the expected relation between the states, which is never necessary to cover more input in the verification. Second, it can efficiently probe the real relations at runtime. Besides, the assertion validation should cover the input space to guarantee high confidence and has a low complexity. However, current work still have some limitations. Take the work of the Liu et al. As an example. It injects controlled unitary gate and auxiliary qubits to implement a non-destructive measurement. They have the ability to check whether a runtime state is in a specific state set. This method is a very representative work to implement a dynamic quantum assertion. However, in terms of expressiveness, it only supports a few operations. Also, it cannot check the relations between states. In terms of efficiency, numeral gates are required to synthesize a controlled unitary gate. More critical, it lacks confident guarantees as it cannot validate the correctness under a few inputs rather than the whole input space. Similar issues exist in other current work highlighted there. The fundamental reasons behind this limitation is the high dimensions of the quantum state and evolutions. Specifically, an n-qubit quantum state can be elaborately represented as a density matrix with 4 qubit elements. By quantum measurement, we can only obtain the diagonal elements and ignore time, moment, and phase. Furthermore, the low confidence originates from the fact that the current method cannot efficiently characterize the mapping between the states in the quantum program. Assume that the input has L qubits and the output has M qubits. When testing each input, it has to traverse the 2 to the n dimension space. And for each input, they need to state tomography with the 2 to the m complexity. An alternative method is to run a process tomography, which requires even 4 to the n complexity, and the n is the program's overall number of qubits, which is usually much larger than that of the input and output. To address these limitations, we propose MorphQPV, and here is his overview. When we write the program, we first pre-label state at the runtime using a trace point pragma. And in the verification, we describe the expected relation between states by assertions. Our assertions follow an assume and guarantee primitive to enable input-dependent validation. And our assertions validate the predicates on classical computer to maximize its expressiveness. And then MorphQPV will validate the assertion automatically. It first characterizes the program to model the neural relations of the states, and it builds classical approximation functions that has a similar behavior as the quantum program. The approximation functions will be simple but accurate. And it will make our validation is performed on this classical function to minimize the complexity. And the MorphQPV validates the assertion by modeling it as a constraint maximization problem. If the assertion is wrong, MorphQPV will output the counter example. And if it's true, Morphy will provide a confidence of the validation. This slide presents some information on the assertion statement. We label the qubit state by a trace point pragma, and we record the time and the prop qubits for each trace point. And the assertion is defined following a assume guarantee format. The assumptions involve two predicates, the P1 and the P2, specifying the range of the state, and the guarantee defines the relation between the states. Predicates are defined as object functions, and it's true if and only if it's smaller than 0. The assumptions means that the assertion means that if the predicates of the assumptions are true, the predicates of the guarantee should also be true. In other words, when the assumption is true but the guarantee is false, the assertion fails. Here we present an example of the quantum teleportation. The input state of a qubit is sent to another qubit as output state in the quantum teleportation, and the assumption is that the density matrix of the input and output states are both pure, and the guarantee is that their density matrix are equal. Then we apply characterization to profile the program's behavior. The characterization of MorphQPV is based on the isomorphism property of the quantum evolution. The isomorphism refers to a structure preserving mapping between two spaces, and this mapping can be inverted. For example, in the classical program, the function y equals x plus 1 is an isomorphism, as it has an inverse x equals y minus 1. And an isomorphism has the probability of the additively and the homogeneity. Specifically, the linear combinations of the function inputs equals the linear combinations of their outputs with the same parameters. And the quantum evolution is also an isomorphism, so they have the same as the additivity and the homogeneity. This enables us to generalize the information obtained from individual sampled inputs to the entire input space. The characterization aims to build a classical approximation functions that has a similar behavior as the quantum program, and it has two steps. First, we sample a set of ontology inputs and record the state at each trace point, and the inputs were prepared by the Clifford group, introduced by Bragg et al. And this aims to ensure the input states are ontology and can be easily prepared. Then we can construct approximation functions. The input of the function is the program input, and the output of the function is the trace point state. And the function computation is based on the additivity and the homogeneity of the isomorphism. For given input, we decompose into the linear combinations of sample input and use their parameters to construct the output. And estimating the accuracy of the characterization is very important as it determines the confidence of the validations. And we propose the accuracy theory for it. The accuracy of the characterization depends on whether the input state can be accurately decomposed. So we have two cases. For case one, for inputs that can be decomposed, the accuracy is 100%. In these cases, the approximation function is the same as the tomography result. And for inputs whose eigenstate cannot be represented in this linear basis, the average accuracy is the number of sampled input divided by the dimension of the space. And we present an empirical result in the quantum teleportation program, and the result matches our theorem. After the characterization, MorphQPV can validate the assertions. And recall that the assertions is specified as predicates of the input and trace point state. The predicates are object functions that are true when the output is smaller than 0. Thus, the assertions can be formulated as a constraint maximization problems. And we want to find the maximum of the guaranteed predicates subjecting to the constraint that the assumptions. And if the maximum is larger than 0, the assertion fails. On the autology line, we have run characterizations and obtain a function for each trace point state. The input of the functions are program input. Besides, we use approximation parameters to represent the input. We substitute the trace point state in the maximization problems by approximation functions, and the arguments of the new functions are only approximation parameters. And the maximization problem can be solved using many solvers. If the maximum is lesser or equals than 0, it means that the assertion is true. And otherwise, maximum argument is the counterexample that violates the assertions. We can estimate the confidence of the validations, and when we do not sample enough inputs. The confidence is defined as the probability that the correctness of the assertion holds for all inputs, which is the 1 minus the probability that the counterexamples are not identified when the program has a bug. And we define an accuracy threshold to discriminate the error. When the accuracy of the counterexample is below this threshold, it will not be identified. And we observe that the accuracy follows a beta distribution. It involves two parameters, beta 1 and beta 2. These two parameters can be obtained by fitting a test data set. And the probability that the counterexample cannot be identified is the red area in the figures, and obtained by integrating the distribution functions. Then here comes the confidence estimation functions with the 1 minus the red area. And note that as we do not know how many counterexamples there are, we assume that there is at least one counterexample and provide a lower bound confidence. Besides, we can see from the functions, when we increase the number of sampled inputs, the accuracies and the confidence increase linearly. And we can finally achieve 100 confidence by increasing the sampled input to a limited number. And we evaluate the MorphQPV. The table compares MorphQPV to pure assertion approach in different aspects. MorphQPV supports the validation of both the mixed state and the quantum evolution by its characterization method. It also supports more comparison type and higher interpretability as it obtains the density matrix of the qubit state on the classical computer. Besides, MorphQPV can verify the quantum program with mid-measurement and simple feedback, as the density matrix can also describe the state of the feedback. We also use 3 algorithms to perform the case study to show our high expressiveness and low complexity. We achieve a high reduction in the number of test inputs and to ensure high confidence. For example, for 20 qubit quantum random access memory, MorphQPV achieves an up to 31,000 reduction to identify the error. At last, we summarize the key points. First, we summarize the limitations of prior works. They have limitations in confidence, expressiveness, and overhead. Second, we introduce MorphQPV to overcome these limitations through a 3-step flow. Third, we introduce 2 key theorems to give an upper bound to the time complexity, and we estimate the lower bound confidence. This paper contains further details on the theorem optimization and the in-depth comparison to prior works. Okay, thanks for your listening, and my presentation is finished.
Hello, thank you for your talk. This is Kushu from University of Pennsylvania, and I have a question about how you can you give me some more concrete examples about how it seems that your mechanism can like try to verify or test like programs with multiple different inputs. But how do you comment? Like I think in most of quantum like programs or circuits, like the input step is encoded in, for example, in the gate parameters, or let's say like for some like quantum machine learning, like the input is encoded in some like initial like rotations. You picked up the like example like the state teleportation, which is kind of very special example to me. Like, how do you think is there any like more examples you can provide with like a program to accommodate need to accommodate very different inputs? Yeah.
Yes, it's a very good a very good problem, and it's a key limitations of this work. But for unitary also can be decomposed into parameter gates. For example, we have proof that n-qubit unitary can be decomposed to four to the n small unitaries, and we can use this method to approximate the functions. But we have mentioned this these things in these papers, and it will become our future works. And we also have a paper about it actually.
Okay, thank you.
So our next talk will be given by Yuhao Liu from University of Pennsylvania, and the topic will be fermihedron on the optimal compilation for fermion to qubit encoding.
Yes. Okay, thanks for the introduction. And I'm Yuhao from the University of Pennsylvania. Today, I'm happy to introduce our recent work from Fermihedron on fermion to qubit encoding. So I guess most people have heard about particles like electrons, protons, or neurons in their physics class. And actually, these particles belong to a large family called the fermions. And the fermions form the fermionic systems. For quantum computer, it is quite attractive because we can actually simulate quantum systems quite efficiently. And many times we have to simulate these fermionic systems. To simulate the fermionic systems, first, of course, we need to capture its Hamiltonian. And the fermionic systems also define a set of these A daggers and A's. They are called the creation and the annihilation operators. These operators form the Hamiltonian, and different fermionic systems define different sets of these creation and annihilation operators. So we know how the Hamiltonian of a fermionic system looks, but how do we simulate it on a quantum computer? So we wish to do the evolution of the systems on the quantum computers, and that's different. So we have to turn the Hamiltonian of the fermionic systems to the Hamiltonian of the qubit systems. But for quantum computers, we don't have these creation and annihilations operators. Instead, we use the polystrings to express the Hamiltonian. So we must find a way to turn the creation and annihilation operators into the polystrings. And this step is called the fermion to qubit encoding. The fermion to qubit encoding starts with the creation and annihilation operators. Suppose here we have n creation and n annihilation operators. First, we'll do a pairing that pairs the creation and annihilation operators to the Majorana operators. So we turn two types of operators into a single type, and this makes the problem easier. And the fermion to qubit encoding finds a one-to-one correspondence between each Majorana operators and the polystrings. And of course, these polystrings must satisfy some additional physical constraints, and we'll discuss about them later. So with fermion to qubit encoding, now we have a path to walk from the creation and annihilation operators to the polystrings. And by that, we could map the Hamiltonian of the fermionic systems to the Hamiltonian of the qubit system. So let's take a look at some actual fermion to qubit encodings. we'll show that with a simple example. Here we have a small fermionic Hamiltonian. And some existing fermion-to-qubit encoding includes the Jordan-Wigner and the Bragg-Kitaev transformation. This is how it looks under the Jordan-Wigner transformation, and this is how the Hamiltonian looks under the Bragg-Kitaev transformation. And here I also show how the creation and annihilation operators and also the Majorana operators are like under the Jordan-Wigner transformation. And one thing to notice that actually this fermion-to-qubit encoding strategy is not unique. So since the strategy is not unique, we may want to study how the final quantum circuit might be, how complex it would be. And a way to measure the complexity of the final quantum circuit is by measuring the polyweight of the qubit Hamiltonian. The polyweight of the qubit Hamiltonian is defined by the number of X, Y, and Z poly operators in it. And in this simple example, we have two qubit Hamiltonian, one with polyweight 6 and one with 4. We can see that the qubit Hamiltonian with lower polyweight corresponds to a shorter circuit. So our goal is quite clear now. First, we need to find different valid fermion-to-qubit encodings. And second, since a qubit Hamiltonian with lower polyweight corresponds to a shorter circuit, we wish to optimize the polyweight of the generated Hamiltonian. And to solve this problem, first, we use the Boolean satisfiability problem, the SAT, to find some valid fermion-to-qubit encodings. Then we proposed a optimization subroutine that we try to decrease the polyweight of the qubit Hamiltonian. And let's see how we do this problem. To solve the valid fermion-to-qubit encodings with the set problems, we have to encode everything into Boolean and Boolean formulas. And to encode the poly operator is quite straightforward. We just use a pair of Booleans to encode each poly operator, I, X, Y, and Z. And for polystring, it's just a sequence of different poly operators. And we also need a few more arithmetic operations of the poly operators. First, we have to get how to multiply two poly operators in the Boolean formulas. And since the coefficient of this multiplication in fermion-to-qubit encoding is not important, we just ignore it. And we could get the formula just from the truth table. We also need to test the anti-commutativity of two different poly operators. And two operators anti-commute if they are different and they are not identity. So the formula can also be obtained from the truth table. Now comes the physical constraints of the fermion-to-qubit encoding, and there are totally 4 of them. And all of them need to be encoded into Boolean formulas so that when we put into the set solver, they need to be satisfied. And we'll go through them one by one. First is the anti-commutativity. So we see that any two polystrings from other strings, they need to be anti-commute. And it is obvious that two polystrings anti-commute if they have odd pairs of anti-commute poly operators. And we already know how to test the anti-commutativity of poly operators. So we test the pairwise anti-commutativity, and we use XOR to get the parity. Since we are expecting odd pairs of anti-commute poly operators, and the outcome should be true. Second, we see that all the polystrings, they must be linear independent. And the polystrings are linear independent as long as they are different. And since they anti-commute, they must be different. And this constraint is always satisfied, so we don't need to worry about it. Third is the algebraic independence, and this one is a bit complex. So it says that for any subset S1 and S2 of all polystrings, their production must be different. So how do we test it? First, we can do the production with what we already have, the rule of multiplication. And we use XOR to test the pairwise equality of the poly operators, and use logic AND to get the final equality of two polystrings. And since the constraint says that we need to get a different result, the outcome should be false. The last constraint is the vacuum state preservation, which requires the annihilation operators maps the zero state to zero. And this can be done by a XY pair in the annihilation operators, since it maps the zero state to zero. So we can test this XY pair one by one and use the OR to get whether there is a XY pair or not. And for the optimization objective, we need to count the polyweights of the qubit Hamiltonian. And counting weight is quite straightforward. So we just add up all non-identity operators, and you see test a operator is identity or not is also quite easy. But the set solver cannot do a optimization problem for a certain value. So we add another constraint. We ask the total polyweight is lower than a certain constant W. We solve this problem recursively, and if there's solution, then we can decrease this constant W and solve it again. But if there's no solution, then we already reached the optimal polyweight. But before we can actually solve the problem, there are a few barriers. First, recall that the algebraic independence. It needs to find any subset S1 and S2, so there are actually exponential choices for them. And we'll see actually we can ignore this constraint. So we did some observation. First, we test the some solutions solved by the set solver without applying this constraint, and the solutions all satisfy. Second, we notice that the poly operators X, Y, and Z in the production of a subset distributed independently. So the probability of two strings to be equal is actually 1 or 4 to the power of n, which is quite low when n is large. So that's why we can actually get rid of this constraint. The second difficulty is when the Hamiltonian itself is too complex. And since we need to count its polyweights, it generates too many formulas. And we could solve this by solving an easier version of the problem. We just count weight of all the strings, and we use simulated annealing to swap the creation and annihilation operators, and try to get a Hamiltonian with lower polyweight. So finally, we evaluated our methods against the Brevik-Kitaev transformation on 3 different problems: the electron structure, Fermi-Hubbard, and the SYK. Both the full set method and the set with simulated annealing achieved great reduction in polyweight. And the reduction in polyweight also reflected on the reduction of the circuit complexity. So our method against the Brevik-Kitaev achieved both reduction in gate counts and also circuit depths. Finally, we tested the circuits of our method and the Brevik-Kitaev and also the Jordan-Wigner on the real IonQ-L2 quantum computer. And since we have the shorter circuits, our results achieved the lowest variance of measurements and also the closest result against this theory. So I guess that's all about it. Thanks for your listening. And if you have any questions, just feel free to ask.
I have one question.
Yeah.
So at the beginning, you mentioned like one of the optimization metric you are using is the weight of the poly kernel.
The weight of the Hamiltonian. Yeah.
Weight of the after the encoding is the poly, right? The how many now?
Yes.
So, but if you really think about the hardware, sometimes not only the weight matters, it also matters like those kind of qubits are closely connected with each other. Otherwise, when you do the decomposition, then like you need to insert a lot of swap gates to get them together. So have you like think about like can you do some co-design between this kind of your optimization with the real hard one in mind so that it will be more practical?
Yes, that is a good question. And actually it matters. So we are not considering in this study, but we are looking forward to do better mapping that considers the structure of the hardware and also the locality of the original physics problems. And yeah we are planning to do that.
Another question is like, I'm new to this area. Okay, sorry. Okay, so instead of like using some machines with a qubit encoding when you have this kind of problem, do you see there is a possibility to have some specialized quantum hardware with like continuous variable like encodings? Is that a better match or like doesn't really matter? Or just high level question?
I guess the physics behind it is just using polystrings.
Okay.
Okay,
Yes.
so I have one question. So you talk about reducing the weight of your poly terms.
Yes.
So, but okay, so let's have this example where I have the ZZII term, okay, so and the IIZZ. Okay, so in one, let's say your method is generating these, whereas there's another method which is generating the all ZZZZ. So it's a 4-weight or whatever. So in the first scenario, you had like two 2-weight terms. In the second scenario, you had one 4-weight term, right?
Yeah.
So, but if I was doing the first scenario, I would still just do the ZZZZ. Just I would execute one circuit and then I would do the measure from that. So, okay, I guess what I'm trying to ask is, are you accounting for what I would actually execute on the device or only in the initial Hamiltonian that I'm generating?
I guess maybe you have some misunderstanding towards the problem. So actually we need to find a one-to-one correspondence between the Marana operators and QM polystrings.
Sure.
So there's no way you can like turn like ZZII and IIZZ into a 4Z. That is a like different solutions.
No. So if I had the ZZII and IIZZ,
Yeah.
now I would not execute these separately when I'm actually running this on my quantum device, right? Because I want to reduce the number of circuits I'm running. So what I would do is I would run maybe like one circuit with all Z's, and then I would just like do some sub-circuit measuring so that, because I would not like execute one circuit for each poly term, right? This is what like the qubit commutativity would do, right? So I'm wondering if you will lose some of the benefits if you're actually doing that.
Well, we actually do execute. How do I say that? So first in the qubit Hamiltonian, I mean, after the mapping, you have you map the creation and annihilation operators to the polystring, right? So in the original fermionic Hamiltonian, so there might be some multiplication terms, and that's where we can find opportunities to do some cancellations between the poly operators. And after you get the qubit Hamiltonians, you still after the totalization, actually we do execute the common circuit for each polyterms.
Okay, thanks. And maybe we can discuss more offline.
Yeah, I think you can discuss the questions offline. So let's welcome our last speaker, Zhang from UCSD. And her talk will be one perk, a randomness-aware compiler for photonic quantum computing. And also congrats on the distinguished artifact evaluation award.
Do I need to connect this?
It's easy.
Hi, everyone. My name is Zhang. I'm from UC San Diego. Today, I'll be talking about our paper, One Perk, a randomness-aware compiler for photonic quantum computing. This work is done in collaboration with Cisco Quantum Lab. Nowadays, we have diverse platforms being developed for quantum computing. For example, superconducting, trapped ion, and neutral atoms. Another interesting platform is the photonic system. Photons can provide very clean systems with low noise because they don't interact strongly with each other. They have great potential scalability because we can generate a huge number of photons continually with time. Moreover, photonic systems can be easily integrated with quantum networks because they both use photons as the information carriers. However, the photonic system is quite different from other platforms. They are more suitable for the measurement-based quantum computing model, which is also known as the one-way model. This is a conceptually different model from the circuit model, but with the same computing power in the sense that they are both universal model. In a circuit model, the computation is realized by applying gates on initial product states, which gradually creates entanglement among qubits. While in the MBQC model, computation is driven by single qubit measurements on an initial entangled state called graph state, which gradually consumes the entanglement between the qubits. The entanglement structure of the graph states varies with the program. For example, for the circuit on the left, the required graph state is shown on the right. Each vertex stands for a qubit, and the edges stand for the entanglement. These edges basically correspond to the CZ gates in the circuit on the left. On the hardware side, photonic hardware is scaled up by a probabilistic operation called fusion, which can merge small entangled states into larger ones if it succeeds. However, the practical fusion success probability is only around 75%, which brings significant randomness to the computing process. For example, if these three fusions succeed and this fails, then the graph state we generate will become something like this. What a compiler does is to construct a program-specific graph states from small entangled states on the hardware called resource states through these fusions shown in purple. And this is performed under the fusion connectivity constraints in a lattice form. In the previous compilation framework named 1Q, the probabilistic nature of fusions was overlooked. Although 1Q can be modified to incorporate a retry mechanism, here green and red stand for fusion success and failures. It requires a sequential fusion executions, making it not scalable. To realize a randomness-aware compiler, we are faced with three challenges. First, the sequential execution of fusions is not scalable. Second, the online pass needs to be done in a very limited time, which is constrained by the photon lifetime in the fiber. Third, there is a structure mismatch between the graph states required by the programs and generated by the probabilistic fusions. Our insights are as the following. First, we can enable concurrent fusions with a percolation phenomenon, which tells us that when the fusion success probability exceeds a threshold, the successful fusions can form long-range connectivity. Since percolation plays a so important role, we name our framework as 1perc, which means percolation-based one-way quantum computing. Second, we can handle the fusion failures by an efficient reshaping of the generated random graph state, which supports a flexible 2+1D structure when the programs are more general and reduces the complexity by a modular design. Third, an intermediate representation can be abstracted to combine online and offline passes and thereby striking a balance between scalability and efficiency. The online pass of our compiler enables the deterministic generation of a 2+1D structure. This structure consists of 2D layers connected in the third dimension, where the connections in the third dimension are flexible in the sense that they are allowed to connect either adjacent layers or non-adjacent layers. For example, if we want to generate a graph state with a structure like this, which consists of 3 2D lattices and 2 edges, one's AC and BD, we can do it like this on a physical level. Each of these 8 layers is called a physical layer. It stands for a layer of photons generated by the hardware in the same time slot that are fused into a lattice structure. Since fusions can fail, some of these edges on the physical layers are disconnected. What we can do is we can find a coarse grain lattice among the successful edges by identifying horizontal and vertical paths among them, which gives us a logical layer. This process is called a renormalization. As physical layers come out continually with time, we try this renormalization on each of them until success. A successful renormalization needs to satisfy 2 conditions. First, the renormalized lattice needs to reach a certain size. And second, we can find a connected path for each required edge between the logical layers. The cross-layer connections are realized with the help of delay lines, which are the green lines in this figure. They are basically some fibers on the hardware that can store the photons for a little while before the fusions. Furthermore, to reduce the runtime latency of 2D renormalization, we can do it in a modular approach where we divide the layer into several areas, renormalizing them in parallel and connecting these areas through the intervals between them. The offline path is mainly responsible for an efficient graph state mapping. The 2+1D structure we mentioned before can be abstracted as a virtual hardware. We map the graph state onto this virtual hardware as compactly as possible to improve the efficiency. This embedded graph leads to an intermediate representation. We call it a flex lattice IR. The IR program is generated before the program execution and will be guiding the online path through a set of intermediate level instructions. We evaluate the framework with two metrics. The first one is the program depth, namely the number of physical layers. And the second one is the number of fusions. These two metrics are relatively independent for 1Q, but are highly correlated for 1perk. So we'll only use the program depth in the sensitivity analysis. Our baseline is the 1Q with the retry mechanism. For each physical layer, we do the fusions of 1Q repeatedly until all fusions are successful. If failures occur in the interlayer fusions, the entire compilation is restarted and repeated until success. We evaluate the framework with some typical quantum benchmarks, including VQE, RCA, QAOA, and QFT. For the fusion success probability, we evaluate with a hyper advanced probability of 90% to see how much 1Q can scale in an optimistic scenario, and evaluate with a practical probability of 75% to demonstrate the power of 1perk. We can find that even with the fusion success rate of 90%, 1Q can only work for small programs, as small as 4-qubit programs in the circuit model. And in contrast, 1perk can scale to larger programs, and the largest scale in our evaluation corresponds to 100-qubit programs in the circuit model. Further analysis shows that the performance of 1perk increases as the size of resource states increases, as the size of physical layers increases, and as the fusion success probability increases. It can tolerate a fusion success probability as low as 66%. The behavior of 1perk keeps stable as the computing scales up, in the sense that as the size of physical layers increases, the average node size of the renormalized lattice is stable, and the program size and as the program size increases, the success rate of renormalization is stable, where we can generate a logical layer with about every 3 physical layers. Moreover, the online processing time is significantly reduced by the modular design of the reshaping algorithm with the resource overhead that the size of the renormalized lattice becomes smaller. To summarize, our work proposes a randomness-aware compiler that achieves both scalability and efficiency for photonic quantum computing. It can tolerate a practical fusion success rate as low as 66%, as well as tolerating photon loss. This is because a fusion is considered as successful only if both the photons are detected. So the effect of photon loss can be considered as a reduction of the fusion success rate. Moreover, our work also provides the potential for achieving fast real-time processing, which paves the way towards the practical photonic quantum computing. That's all. Thank you so much.
Thanks for your wonderful presentation. I'm Dawei from University of Pittsburgh. I have one question about your work, which is that in each time step, you're trying to use the fusion to generate a bigger 3D structure of the graph state, which contains resource state with more entangled qubit, photon qubit, right?
Yeah.
Because you consider the randomness in your framework, so let's say if in the current time step, one fusion fails, then you need to use the spare photon qubits to retry this operation over and over again, right? So I think there still exists the probability that after using all these available photons, the operation you need to execute in the current timestamp still fails. So it means that you need to regenerate the whole 3D structure in again, and which will change the topology and the shape. Then it means that if you need to utilize the photon you want in this step, will be generated in the different location, right?
Mhm.
So maybe there's the need to come up with a backup plan to use some swap or some likewise operation to transfer these photons you need to the destination location. Is that a necessary idea for your framework?
Okay, you mean using swaps between?
Yeah,
the
because
photons?
the photons you need is in the different location
Yeah.
after you generate a different structure, right?
Okay, maybe let me first clarify. The process you mentioned just now is, to me, is more like the 1Q plus retry. I'm not sure if I misunderstood, but for 1PERC, we didn't really have the process of retry. Let me briefly. Yeah, it's like this. So all of these layers, they come out from the hardware continually, and we try the renormalization again and again. And because we have the percolation theory, it tells us that it is very likely, it's a very high probability that the renormalization on each layer will succeed. And we just wait until the renormalization succeeds and see if the interlayer connections can be found. If both these criteria are met, then we consider it as a successful renormalization. And for the structure, what we do is like before the program execution, we already map this graph state onto the hardware to make sure that it satisfies the constraints of the virtual hardware. So in the runtime, we already know what edges we want to generate, and we just repeat that renormalization and wait until those edges are connected. Is
Okay, I
that
see.
more clear?
So it means the location of each photon you want in the next timestep is fixed when you
Yeah,
generate.
the location you mean, I think, is the structure mapping we do before the program execution. Yeah, for the offline pass, we resolve all the connectivity constraints you mentioned here. And for the online pass, we just want to move as fast as possible. So we just do this rigid lattice structure, and because it's faster. Yeah.
I see, thank you.
Okay,
Thank you.
great. Let's thank our speaker again. And that's all for today's session on quantum computing. And thank you for coming again.
Thank you so much.